Sylvie Nadeau. I am full professor and director of the Applied Human Factors Lab at the Mechanical Engineering Department of École de Technologie Supérieure in Montreal. I'm also director of the master's program in Occupational Health and Safety Risk Engineering and faculty representative of the Academic Council at the same university. I'm a member of the scientific committee of the Intelligent Cyber Value Chain Network in Canada and co-chair of the IEA Resilience Engineering Technical Committee. We are pleased to have you with us to share this first presentation of a series of 4 on systemic methods in complex and digitalized manufacturing, a webinar series organized by the Resilience Engineering Technical Committee of the International Ergonomics Association. Today, Dr. Yanel Torres will share his collaborative work on using STAMP-STPA in a real case of complex manual assembly in aircraft engine manufacturing. This presentation is based on an earlier journal paper published in the Human Factors and Ergonomics in Manufacturing and Service Industries journal and funded by the Natural Sciences and Engineering Research Council of Canada and MITAX. Before we kick things up, I have a few housekeeping items. We are expecting this webinar to last about 60 minutes. IEA is recording this webinar, and it will be made freely available on the IEA website. We encourage you to send questions and comments throughout the presentation using the Q&A feature and use the chat feature for administrative issues. I will be managing the Q&A, and we have time reserved at the end for answering your questions. I will now give you a few details about our speaker. Dr. Yanel Torres holds a PhD in engineering from École de Technologie Supérieure in Montreal, where he focused on reducing assembly errors in the aerospace manufacturing industry. With over a decade of experience, Dr. Torres has collaborated with diverse industry sectors, including aerospace, biotechnology, hospitality, and energy. His current research encompasses systemic approaches to manufacturing, the application of industrial exoskeleton technology, and the impact of fatigue on human error. His work is featured in various international journals, and he is a member of the Quebec Board of Engineers, the Association of Canadian Ergonomists, and the Colombian Society of Ergonomics. Dr. Torres remains committed to the interdisciplinary research, engaging with academic and industrial partners to advance safety and ergonomic practices. Welcome, Yanel. I will let you take it from here.
Hi, everybody. Good morning. Thanks to Professor Nalo for this introduction. I will be sharing my presentation. So here, you should be able to see the presentation. Please.
Oui, ça va bien.
Okay, c'est bon. So, good morning or good afternoon, good evening, depending on where are you located in the world. I would just add to the introduction that Professor Nal has done, that I'm currently assistant professor at Universidad de Antioquia in Medellin, Colombia, where I'm located right now. I'm also adjunct professor at the École de Technologie Supérieure in Montreal, Canada, where I did my PhD and master. Today, I will be talking about the application of a systemic method to complex manual assembly, specifically aircraft engine manufacturing. We will be focusing on STAMP-STPA, but also we'll be presenting briefly some other application of systemic method in order to put STAMP-STPA in perspective. I will be doing a very short introduction. important to let's say to remark that this research that I'm presenting today it's already published in the literature in the journal Human Factor Ergonomics in Manufacturing and Service Industry. Here I place a QR so you can scan and download the document of the paper, so you can get a deeper understanding and dive into the result that we have done, the research we have done. The objective of this presentation, there are three main objectives. First of all, to show the impact of human error in manufacturing in general, but specifically in terms of quality, defect, and issues when workers are confronted with complex manual assembly. We'll see what is complex manual assembly and why it's so challenging for workers when they face manual assembly task. Second objective, to present the application of STAMP framework in a realistic case of complex manual assembly, contrasting this method or approach with other systemic method, specifically AcciMap and HVAC. And of course, the idea here is to encourage broader reflection on the value of systemic approach in the context of manufacturing as a general sector, but specifically in complex manual assembly in relation with assembly error and defects. This presentation, however, relate to classic assembly case used as a starting point that's important for the analysis of Industry 4.0 technology through a systemic approach. That's important to make this remark because this is a webinar series, and the next presentation, it will be 4 presentations, but the first presentation is focused mostly on classic manual assembly, but there are some other presentations that will focus on digital technology in the context of Operator 4.0. So that's important to make this remark. I will not get a deep dive into the theoretical conceptualization of human error, but I bring here a short definition of human error as presented, defined by Sanders and Morai, where they define human error as something that has been done which was not intended by the actor nor desired by the set of rules or an external observer, or that led the task or system outside its acceptable limits. There are several definitions and also debates about human error, but it is actually a category of human behavior that has been explored extensively in the literature. And in this slide, I want just to point out that human error can manifest in real context in different ways. I identify 3 major ways that human error can manifest. First of all, major accident. This is well known because of accidents like Chernobyl, Exxon Valdez, and many other major accidents in safety critical sector. But human error can also translate or manifest as occupational accident that occur day after day in different general sector, like for example, construction. So these are 2 examples of how human error can manifest, the kind of outcome that you can expect from human error. In healthcare, you have a specific type of outcome, which is our adverse events, which are managed in a specific way because of the characteristic of this context. And in manufacturing, you also have quality defects, particularly when you have manual assembly, when you have workers who are performing the task to construct, to build an object or product in assembly line generally. So these are different, let's say, manifestation of human error, the same phenomenon. But here we are addressing mainly or exclusively quality defects in manufacturing. That's what is our object of analysis. What is complex manual assembly? It's important to just have a brief definition. It's a kind of assembling task. Actually, it's an assembling task that requires a specific knowledge and skills from the worker to complete the task. Also, in general, assembly object consists of a high number of parts with a high number of possible choices, while the geometry of the assembled object has several symmetric planes. So this is what we are referring to as complex manual assembly. The main feature or characteristic of this kind of assembly is the high cognitive demands that it imposes on the worker. Here in the literature, you can find two main way of defining complexity in relation to manual assembly. Static complexity, which is mostly related as with the object in the phase of design, is an intrinsic attribute of the object to be assembled. And you have dynamic complexity, which is a context dependent. So when we are talking about dynamic complexity, we are referring as the complexity that arise or emerge in the interaction between the human, the object to be assembled, and also the context environment, the instruction, and how the system is managed. So that's important as a theoretical framework. So now we will be presenting a little bit or addressing a little bit the subject of manual assembling in manufacturing, specifically because manufacturing has different, let's say, domains, one of which is manual assembling. In manual assembling, there is a relationship, a close relationship between human error and quality issues. And in assembly system in general, product quality can be affected by a high prevalence of human error. So you have a high rate of human error that translate in a higher number of quality defects, and it can affect also productivity because of rework and scrap part and need to be scrapped. And an analysis conducted by Falk and colleagues in Sweden, in actually was in a Volvo plant, the author found different or several assembly error. Among these error, they found component installed in the wrong position, improperly tightened part, missing screw or other essential component, tubes or wires connected incorrectly, scratch, dirt, or other surface damage on component, contamination within the assembly. So these are examples of the kind of error that manifests as quality issues in manual assembly. This is from car manufacturing, but it can happen also in any other manufacturing environment, and regardless of the product that is produced. Here we have a picture, an image from the Volkswagen e-Golf factory in Dresden, Germany. So here we can see that are at least three workers who are in some way doing as a manual assembly task. Even though manufacturing is in car manufacturing is a heavily automated industry, we still have part which is very manual assembly intensive, let's say. So important also from a behavioral perspective that manual assembly occur, or human error in manual assembly occur most of the time at the skill and rule level of human behavior. Here I'm presenting the well-known model of skill rule knowledge of human behavior proposed by Rasmussen in 1983. And here you have three levels of human behavior, and error can occur at each of the three levels here. in the model, but it depends of the task, because human error and manufacturing, or let's say manual assembling in general, are carried out within a structured and predictable environment. That means that, for example, knowledge-based behavior error are, let's say, inexistent or very, very low, because this error occur when people or workers are confronted with unexpected situation, or a situation where they have to make a decision based on information that is not completely available. So these kind of situations are rare. So that's why most of the time the kind of error that arise in manual assembly are mostly slips related with attention, lapses, or related with memory, and rule-based mistake. That's important to to consider. To have an idea uh, of, let's say, the kind of workstation and manual assembly that we are talking about, I put here an image that provide you an idea of the assembling object. This is an aircraft engine. Here you have an assembler, an operator, and you have different components, several components that need to be placed correctly and in the structure of the aircraft engine. Important, you have some example, for example, fixation brackets, which are indicated by the red arrows. These brackets are used for fixating cables, tubes, and different elements to the structure of the aircraft engine. You also have cushion loop clamps. These cushion loop clamps are used to attach actually cables in a properly way. You have also caps and covers, which generally are yellow in color, lock wires, bolts. So there are plenty of assembly part that need to be properly integrated in the assembly structure. These are referred frequently as externals. Externals are all these components you add to the structure of the aircraft engine toward the end of the assembly process. So that provides you an idea that the worker is confronted with hundreds of or thousands of parts, and you can also have an idea of the planes, how the geometry of the assembly object is very, let's say, complex in nature. I mentioned before that today we are talking about classic manual assembly, because let's say here I have an example of a diagram of what classic manual assembly look like. But basically you have a work cycle, a worker that will read the work instruction on the computer, on the workbench. It will select part from the containers. It will retrieve the necessary tools, perform the assembly operation, and will close the work instruction on the computer. This is a simplification, but it provides you an idea of the work cycle related with classic assembling and how interaction it happens actually. This is different from smart manual assembling. That's the way of call this kind of assembling, where the worker is, let's say, supported by technologies, like, for example, augmented reality. It could be with the Google's, or augmented reality with light projection. We'll have smart tools, cobots, smart glove, 3D instruction, virtual reality for training, machine vision for support decision making. So this is a context more related with Industry 4.0, and that will be addressed in this webinar series in the next, let's say, presentation that will take place next Saturday, and so on during 3 more Saturdays, let's say. So that's the main difference. It's important to do this remark from classic to the smart manual assembling, or digital assisted manual assembly. In classic manual assembly, you will have something like this. A worker will read instruction in the computer. Here is an instruction where you have a drawing, basic one, and you have steps that you need to complete. That, for example, here you have three brackets. Let's take the bracket A, that the one you have to place properly on the structure of the aircraft engine. And what can go wrong? Well, the bracket can be placed in wrong direction or in a wrong place or in a wrong side. Also, it could be the case that there is a missing bolt or washer or a loose bolt. So this is a few examples of what can go wrong in terms of human error, which will generate a quality issue. So that puts you in context when we are talking about complex manual assembling, aircraft engine manufacturing and assembling. What are we talking about, and the kind of challenge that the worker is facing actually. So that's was the objective of this part, is to present and to put in context the audience about the context or the object of study. So from a methodology point of view, I will briefly present what was the methodology that we follow in order to achieve the analysis with systemic method, with the STAMP framework, and the other one too. Basically, our methodological approach, is important to remark that the systemic uh, analysis with this method STAMP framework was only a portion of the entire research. So we start by collecting data and field information. We conduct a human reliability analysis. We explore in depth relevant factors like workload, fatigue, shift work, and as a last step, we conduct system analysis or analysis with systemic method, STAMP, AcciMap, and HVAC. Actually, all these analysis and data and field information was a part of a one-year project at the Industrial Partner Facility. So myself, I was working closely with the industrial partner. I had access during one year to different stakeholders, manager, workers, and data and database. So we conduct statistical analysis of quality record, study of work instruction, systemic observation of worker in the field for a better understanding of the task. Uh, we conduct on structure interview and observation visit, meeting with line supervisor, manager, workers, discussion preliminary result. So it's important to understand that it was a project that was closely related with the partner, and we had access during a long time to the industrial partner facility. We did actually human reliability analysis, which aimed to identify and quantify the likelihood of human errors, so the probability of human error, in order to optimize safety, quality, and productivity. However, human reliability analysis focuses on task and goal-related human behavior. It lacks a systemic view of error. That's something that was lacking. So ARA focused mostly on the worker and the factor that influence performance, mostly related with the work context and environment. That limits in some way the understanding of the interrelationship of influencing factors. So, because yeah, you can identify influencing factor with HRA in general, but these influencing factors are closely related with the immediate environment of the worker, and you don't have the interrelationship from a broad perspective. So although we conduct HRA and identify key influencing factor, the big picture was still missing. So that's why we we went for the systemic approach and systemic method. Briefly, in system approach analysis, what will provide, or what kind of insight can we get from this kind of approach? Error-related quality deficiency are seen as systemic phenomena that result from the interconnection between multiple contributing factors at different level of the organizational system. So we are moving beyond the worker and beyond the factor directly related with the worker task through the entire, let's say, manufacturing system. So several systemic accident analysis methods have been developed in the literature. We have AcciMap, STAMP, HVAC, FRAM, but all of them have been intensively applied in safety critical sector, and most of the time oriented toward the analysis of accident. So the risk and the factor influencing accident as outcome. But here we are talking about quality deficiency as outcome of human error. So as we have done a literature review, at least in Spanish, French, English, we are the first one who are applying this methodology to the context of manufacturing and complex manual assembly to the best of our knowledge. So the usefulness of this method in manufacturing context, when we start to applying this method, still under discussion, although we already have provided some insight about the usefulness of this method. The STAMP-STPA is important to remark that this is a framework that was developed by Professor Levinson in the MIT in the United States. And what is the difference between STAMP and STPA? The STAMP actually is a model that provides a systemic view of safety, emphasizing that accidents result from failure in control loop. The STAMP, that means system theoretical accident model and process, while STPA is a structured technique within the STAMP framework designed to identify unsafe controls, action, and scenario that could lead to accident. We actually are presenting today the application of STAMP. STPA provides more detailed analysis of unsafe control action, causes, and scenario, but STAMP can also be used as a standalone. That's important to do, to notice, because sometimes there's a little bit of confusion, but you can use STAMP as standalone also. So here you have the general form of a model of a sociotechnical system control structure that is proposed by STAMP. So this is the way that STAMP proposed to model the sociotechnical system. It provides actually a broad understanding of the systemic failure based on control loop interaction. Because a STAMP framework is based on the control theory, very related with system engineering and the field of automation in the engineering, let's say, discipline. So this is how STAMP proposed to see the structure of a model of a sociotechnical system. But it also provides a taxonomy of control loop failure. So, and that's the one we use to identify how a different kind of failure can arise during the assembly process. So here there is a representation of a control loop with a controller, actuator, the control process, the sensor, and also different types of failure that can arise during this process. In our case, the control process was the assembly process, the complex manual assembly. We will see that in a few minutes, because what we have done is that this taxonomy, we translate that in our case of what kind of failure can arise in our case. So in terms of result here, we have the sociotechnical system of the manufacturing system where that we were studying. Of course, we have control process at the bottom of this structure or sociotechnical system. We have the assembly, the actuator, sensor, and assembly process that we will see at left more details. But we identify at least three main controller. The first one at the left is engineering, design, and development. Also production and quality management and manufacturing IT system management. These were the three that were relevant in our context because, for example, one thing that we identified were issues in the assembly instruction, several issues, and assembly instruction came from manufacturing IT and system management. Manufacturing IT are responsible or in charge of developing the assembly instruction and providing the assembly instruction through the manufacturing execution system. So we identified several issues in that case. So that way, for example, here in the control loop, you have computerized assembly instruction that came from manufacturing IT and also system updates and user guideline and training. Those are an example of the input that need to be that came from manufacturing IT. And you also have feedback that need to be provided that sometimes is not provided, but need to be provided. Like for example, system user and performance report and user needs and requirements. So instruction ideally need to be developed by manufacturing IT based on the final user needs. Actually, the final user in this case is the assembly worker. And also the requirement need to be obtained from assembly process. But sometimes these control loop fail and actually the structure are not provided properly. So this is an example, and you can see also from production and quality management, production progress report, quality issues, that's feedback that came from the assembly process. And also you have supervision, production schedule, tools and equipment. That is the input that production and quality management need to provide properly to the assembly process. So that's briefly how this work in the case of the control loop that we have at the bottom. You can see at the left that controller actually would be the worker, the assembler, and the mental model of the assembly process. You have actuator, the assembler's hand and tools. This is a manual operation. The control process is the assembly step, task, and sensor. It could be the assembly sense, but also measurement tools. There are some tools that provide feedback on the measurement of some value, for example, torque range. So this is the big picture of the sociotechnical system. And after that, we identify the control loop failure, but more related with the assembly directly as the control loop at the bottom of the process. We identify, for example, deficiency in the design delivery of assembly instructions, as I mentioned before, and at the controller level, let's say the assembler failure that can arise are, for example, mental model of the assembly operation inconsistent, incomplete, or incorrect. So this is the cognitive aspect of capturing information from the assembly instruction and creating a representation of the assembly that you need to conduct in 3D. So although the assembly instructions are provided in 2D as a drawing, not very, let's say, realistic. So this is the kind of failure in the control loop flow in the creation process of the execution plan for assembling. We here in the control process, for example, at the bottom, we have variation in production level and workload. We identified that as an issue. And that was related with some instability in suppliers. So at that point, production was very uneven, and some weeks the production level was low, and some weeks the production level was high, and that introduced variability. Let's say there was not stable production level. Workflow, that's what we call workflow discontinuity, and of course, we have the a controller who is the assembly line supervisor that acts as another controller that is responsible for production planning and overtime. So these add the variation to the workload because, for example, when during a week of high production level, there was a need for overtime, and the how the overtime was distributed among workers was, let's say, assigned by the assembly line supervisor. In some cases, workers would have a high level of workload in terms of overtime. So also we identify, for example, lack of tools with adequate tracking of feedback. So actually in classic manual assembly, what we have are very classic tools too, and very few smart tools. So probably not at all. So that was a very issue because let's say the supervision or the identification of issues was mostly done by the workers. So there is no assistance from tools. So this is in short the kind of failure that we identify in the control loop of the assembly process. And before I present the sociotechnical structure and also the different feedback loops and also the inputs that at different level in the sociotechnical structure. We also apply AcciMap and HVAC, which both of them provide different insight because we will see the underlying theoretical let's say, ideas are different from STAMP. The theoretical framework is different. In the case of AcciMap, you don't have any taxonomy, so you only have six level in the system, and you need to place there factors that contribute to, let's say, in our case, to human error or assembly issues, defects, but you can relate them with arrows. In case of HVAC, you have a taxonomy, you have four levels, but when you do the analysis, there is no relationship between the factor at different level, at the upper level with the, let's say, a level that is under at different level. So you don't have connection to make here. So, but it provides you a taxonomy. So here, briefly, this is, for example, for error-related quality deficiency, you apply AcciMap. This is a sample because the AcciMap was bigger. You have, for example, fatigue as a factor we identified during the human reliability analysis that was present in this situation. That could be associated with excessive overtime, as I mentioned before, because fluctuation on production demand, and that was generated by the staff scheduling and overtime allocation, high level of production, and at the end, this is related with unstable part supply, so a problem with supplier. But it could be also related with external, with sleep habits, so the amount of sleep that workers are, let's say, getting. So this is the kind of analysis that you could do with AcciMap. How it's presented, you don't have a taxonomy, you only have 5, 6 level, and you place the factor you identify at different level, and you relate those factors. In the case of HVAC, basically it's only a list number of let's say factor at different levels. You have organizational influence, supervisory factor, and precondition for unsafe act. And you have also the unsafe act, which are actually the assembly error. So, for example, supervisory factor here we identify inadequate supervision, failure to provide guideline on shift scheduling over time allocation practice. So, the shift work scheduling that supervisor were conducting disregard the principle of prevention or mitigation of fatigue. So that was because of a lack of knowledge on how to best do the overtime allocation and shift work schedule. So that's an example of kind of supervisory factor. The good thing with HVAC is that it provides taxonomy, so it can guide you in some respect. In terms of precondition for unsafe act, we found high task complexity, the use of low fidelity to the image, flow in the assembly instruction delivery system, as I mentioned at some point, and limitation of visual inspection. And interestingly, with HVAC, you have a factor at higher level in the organizational structure that are related, for example, with operational process, like the lack of integration of end user requirement to the manufacturing execution system, or the instability in the part supply chain that's related with the suppliers. So this is something that is higher, but we found that can have a significant impact on the performance of worker. Also, for example, the budget priority allocation, because IT strategy needs significant fund for technological upgrades. So the idea that assembly instruction can be changed easily, that's not true. It's very heavily intensive to change and upgrade all the manufacturing execution system to provide more realistic and more ergonomically designed assembly instructions. So it's a lot of budget, but of course that the IT strategy and how they allocate budget influence actually the quality of assembly instruction that the worker is receiving at the working station. So this is an example of how HVACs actually work. Putting STAMP in perspective, which is the framework that we are concerned today mainly. We put here a table that make a short comparison between AcciMap, HVAC, and STAMP. They have different underlying model. STAMP is based on system control theory, while AcciMap is based on organizational hierarchical structure. HVAC is using Swift-Cheese model, and well, some of them they have a taxonomy, some of them no. Like for example, STAMP as a taxonomy, HVAC yes, but AcciMap no. And the level of expertise required in general is low for AcciMap, medium HVAC. For STAMP is high because you need to understand what the control loop is, the taxonomy, and so the level of expertise required is high, and all of them require a high level of availability and access to information. So this is not a method that you will do an analysis based on 2-3 information that you have from the let's say the situation you are analyzing. You need in-deep understanding of the system and access to data and information. So because we are here presenting briefly also validity and reliability, it has been pointed out in the literature that the qualitative nature of STAMP and other systemic methods negatively impact the reliability. Of course, it depends how you understand reliability and validity, but that's something that has been pointed out in the literature. For example, Hulme and colleagues in 2021 found that systems-based accident analysis in general, this kind of method did not produce satisfactory validity results compared to an expert analysis used as reference. But I want to point out here that there's a difference between analytical method and evaluative method. The systemic analysis methodology or framework, they are analytical method, not evaluative method. So sometimes we are trying to evaluate validity and reliability of analytical method based on a paradigm of evaluative method. For example, the main objective when you apply AcciMap, HVAC, or STAMP is to understand, to explain, to model the system. But evaluative method, in contrast, they focus on assess judge or determine effectiveness. So they need to provide value to take decisions. So that's one of the main differences. So the natural are different in analytical method. We are in a exploratory and explanatory, let's say, way to do or to approach the situation, while evaluative methods are more applied and normative. So it's important to make this distinction. So how we try to ensure, in our case, validity and reliability. So methodologically, we follow a triangulation approach where we use mixed method. We use qualitative empirical method like observation, interview, focus group. Analytically, we use systemic modeling method and also quantitative empirical. We use inferential statistic, descriptive statistic, prediction model. So we use a mixed model approach. Important to also to consider that our research constitutes a case study. It allows for the analysis of specific problem within well-defined context. So it's important to clarify that. So our results need to be understood in relation to the context that they emerge. So complex manual assembling in aircraft and gene manufacturing. So systemic method, in our case, were used to discover new relationships previously unseen within a given reality. So we seek to develop actually an understanding of the sociotechnical system of the study rather than verify a predetermined hypothesis. So that was our approach. We had some enabling factors in the research context, so factors that give you positive regard to this methodology. One of them is the fact that we conducted during 1 year internship with the industrial partner. So the researchers had direct access and recurrent access to field and direct contact with workers, supervisor, manager, and all necessary data. And our results were presented to manager, to worker through the research process. So prior to the analysis, using the systemic method, because the systemic method was the last step in our research, we conduct other analysis with human reliability analysis, analysis of quality defect report, statistic of assembly error, study of fatigue, and blah, blah. So all these analysis and data and information serve as input for this systemic analysis that we conduct as last step. So we did probably dozens of follow-up and validation discussion were held with the supervisor, quality manager, production manager, IT manager, and also the worker. So that provide us solid, let's say, validity in what we were doing. And final consideration about the research we did, well, systemic method, we found that allows to focus the analysis on manufacturing system failure, so to have an idea of the big picture rather than on an assembling worker's error. So we shift the focus. The analysis of operational risk, generally in manufacturing, like quality deficiency, we also argue that can benefit from systemic thinking approaches and methods. So there is some value there to do this kind of analysis in order to model the behavior of the manufacturing assembly system. We're not talking about the behavior of the worker, but the behavior of the manufacturing assembly system using this system thinking method implies that's something that need to be considered, a relatively high level of knowledge about the system itself. It's not like someone will do this kind of analysis going 2-3 times to the production facility and getting few information or data. It's hard to do something valid in that regard. It is argued actually that within the Industry 4.0 transformation, the system thinking approach, the system methodology, may provide the needed support to build a resilient manufacturing system. That's something that we argue and that we will be exploring in this webinar series. So acknowledgement, the industrial partner, École de Technologie Supérieure, National Science and Engineering Research Council of Canada, and MyTech Accelerate program, which provide funding and access to to facilitate. So now, thanks very much, and I invite you to take a look to our publication from the Applied Human Factor Lab, which is, let's say, Professor Nadol is the head of the lab, and here with this QR, you can go to ResearchGate and to take a look to the publication we have done. So thanks very much.
Thank you, Yaniel. Now we have 10 minutes for the question period. Do any attendees have questions? Please use the Q&A section so that we can answer 2 questions. Okay, there is no questions in the Q&A. So I will close this webinar. So thank you very much, Yaniel. Thank you to the IEA. Thank you to everyone for joining this webinar. And please join us February 5th. It's not a Saturday, it's a Wednesday, for the second presentation of this series, showcasing the research results of the members of the Resilience Engineering Technical Committee. Our speaker will be Ari Andriansen, and he will share his collaborative work on FRAM, STAMP, and EAST, and a case study of a collaborative robot. Please note that attendees will receive a web link for a post-webinar survey, and an attendance certificate will be delivered if you respond to the questions correctly. Thank you very much, and have all a nice weekend. Bye-bye.